Section 13.3, probability and odds. We're going to start and focus mainly with probability. Probability is the likelihood of an event occurring. You've probably seen probability if you've ever watched poker on TV. If you see those percentages, that's probability in real time. The probability of a storm happening, like if you watch the weather, that's a little bit different because the sample space, the set of all outcomes is a little bit different. The probabilities of those events occurring is calculated a little bit differently. But for what we're talking about, we're thinking more of the number of outcomes. So the number of outcomes, all of the outcomes in an experiment, whether it's drawing a card or flipping a coin or rolling a dice or spinning a spinner, whatever it might be, all the outcomes possible make up what's called the sample space. So if we think about drawing a card, if we're drawing just one card from a standard deck of cards, there are 52 outcomes because there's 52 different cards. If we're flipping a coin, heads and tails makes up our two possible outcomes. So our sample space could be fairly large, it could be really small. Okay, it really is just going to depend on the situation. When we have a successful outcome, or what we deem to be a successful outcome is, or a desired outcome, whether if we're looking for a heads or we're drawing a heart or something like that, that's called a success. And anything that we don't want to happen, that's going to be called a failure. And you're going to find that in any textbook, on any website, just kind of a basic general information on probability. Now, how you calculate probability, the probability of an event, this is how you say it, the probability of an event, whether it's drawing a heads or flipping a tails or rolling a 2, whatever it might be, what you want to have happen will be inside the parentheses. It will always be a P, so it's going to look a little bit like permutations, which is why when we do permutations, I would rather see like NPR, but that's just kind of a side note there. So we'll just see probability of an event is equal to, how you find the probability of an event, it's the number of successful outcomes, so we'll say SUCCESSES, successes, over total outcomes. So if we're looking for the probability that we draw a heart out of a card, there are 13 hearts out of 52 total cards. We could simplify that down into 1/4. That would be a real brief example of finding probability. So we're going to keep this fraction in mind a lot. Successes, the number of successes or the total number of outcomes, and that's going to be how we find our probability. Now, we can leave it as a fraction, we can write it as a decimal, and we can write it as a percent as well. And we'll talk about that here in just a little bit. So let's jump right into an example. There are approximately 100 million households in the U.S. 5,000 of them are randomly chosen to be a Nielsen house to measure TV ratings. What is the probability that your house is selected to be a Nielsen house? Hopefully you've heard of the Nielsen ratings before. That's how they determine, when they say 16 million people watched the Super Bowl last year, they're basing that off of the Nielsen ratings. They take what the 5,000 people that they surveyed did, and they just kind of scale that up to the U.S. population. That's kind of how they determine how many people watched a specific event on TV. So we got 5,000 people. We're randomly choosing a house. What's the probability that your house is selected? So we're going to say that a success is that your house is chosen to be. So we're going to say the probability of that your house is selected. Probability that your house is selected is equal to how many houses are considered successes? There are 5,000 Nielsen houses. And how many houses total, or how many households total in the U.S.? That would be 100 million. So 100 and then 6 more zeros after 100. So 100 million. If you want to simplify this down, you certainly can. The 3 zeros on the 5,000 and the 3 zeros on the end of 100 million cancel each other out. So you're down to 5 over 100,000. That can be simplified farther into 1 over 20,000. That's just a little extra side note there. If you want to write this as a decimal, feel free. This would be 0.000. I got to make sure I got my notes right here. This is 4 zeros and then a 5. That's the decimal. Remember, turning decimals into percent, we move the decimal place 2 to the right. So this would be 0.005%. So there's several different ways you can write this. You could write it as 1 over 200,000. You could write it as 0.00005, or you can write it as 0.005%. Lots of different ways to write it, all of which are correct. Now, as I said, when we write it as a fraction or as a decimal or as a percent, the only one that's not going to be included in this part is the percent. Probability is always between 0 and 1 inclusive. So this goes more for the decimals and the fractions. We can kind of think of probability on a number line. Okay, so here's 0 out here. I'm actually going to put this up here. So 0 is here, 1 is here. So probability can go from 0 to 1.5 then obviously would be in the middle, so 0.5. Anything with a probability of 0 is something you could say is never going to happen. Never going to occur or happen. OCCUR for occur. So something with a probability of 0 is never going to happen. A probability or something with a probability of 1 is something that is guaranteed to happen. Hopefully I get enough room. Guaranteed to occur. Okay, if a probability is 1, that means it's going to happen. So the probability that you flip a heads or a tails is 1 because it's either one or the other. If we think about rolling a dice, and if we want to say what's the probability we get a number that's less than 10, well, the probability there is 100 or 100% or 1, because all of the numbers on a dice are between 1 and 10 or less than 10. If something has a probability of 0.5, we can think of that as a 50-50 chance. Okay, 50-50 chance. The closer we get to 1, the higher the chance it's going to happen. The closer we get to 0, the less likely it is something to happen. Let's try a couple more examples here. A sock drawer contains single unmatched socks. 19 of them are white, 8 are black, and 5 are blue. Question number 1, what's the probability that a randomly selected sock will be black? All right, so we're going to write this out. We're going to do probability, P, and in parentheses, I'm just going to write black. If you want to write black sock, that's fine. How many black socks are in the drawer? Well, it tells us that there are 8 black, so probability there are 8 possible successes or 8 successful outcomes. How many socks total are in the drawer? Well, we need to add up all the socks. So we have 19 white and 8 blue. That makes that'd be what, 27 socks total plus another 5 blue ones. So 27 plus 5 makes, that would be 32. So 8 over 32. Again, this is something we can simplify, so we can say it's 1/4. That would be the probability. If we want to write this as a decimal, that's 0.25. If we want to write this as a percent, that would be 25%. So the probability that we get a black sock when we draw one randomly out of this drawer would be 25%, or 0.25, or 1/4. Question number 2, what's the probability that the randomly selected sock will not be white? Now we got to think about a little bit different. So I'm going to write this in blue. So the probability that we're not going to get a white sock. Well, how many socks in the drawer are not white? Well, we could be black with the 8, or we could have blue. So we need to actually add those two numbers together. So we're going to have 8 plus 5 over, still 32 socks total in the drawer. 8 plus 5 makes 13 out of 32. I don't believe 13 out of 32. 13 over 32 can be simplified. If you want to write this as a decimal, let's write it in 3 decimal places. So that'd be 0.406. And then as a percent, if you want to turn that decimal into percent, that would be 40.6%. That's a pretty basic example. Let's try a little more. Let's try one that's a little more complex. So, a box of 60 baseball cards contains 8 cards with errors on them, whether that's misspelled name or incorrect statistic or wrong team or whatever it might be. 8 cards with errors on them. If 5 cards are selected at random, what's the probability that all 5 cards have errors? All right, this one's a little more complex. So we're looking for the probability that we get 5 errors on our 5, whoops, let's spell errors, right? See, there's an error right there, errors, okay? If we think back to our definition of probability, this is the number of successes over the total number of outcomes. Now, the question here to me is, how do we define a success, or how do we figure out what a success is? Well, to me, there's 8 cards we need to pick, and because it says there are 8 cards with errors on them, we're choosing 5 of them. It doesn't matter what order we pick them in. So this is a combinations problem. So we're kind of getting back into previous sections. So to me, a success, or how we find the number of successes, we have 8 failure cards or 8 error cards, and we need to choose 5 of them, because that's going to be the number of ways that we could have 5 error cards. Okay. The total number of cards, well, it says there are 60 in the box. Again, the order in which we pick them doesn't matter, because we can rearrange the order. It doesn't matter. We're still choosing 5 of them. So the total number of outcomes, the total number of ways to draw 5 cards is going to be 60 choose 5, or 60C5. Now 60C5 is a massively large number. Okay, so this, I'm actually, before I write these numbers, it might help to write these little notes. Hopefully I got enough room. How many ways, I'm going to kind of write over my writing here, how many ways to choose the error, 5 from the errors. Choose 5 from the errors. Okay, that's what this number tells us. And then the 60C5 is how many ways to choose 5 from our box. 5 from our box of 60. That's what this tells us, okay? So just so we have a little side note where we're getting these numbers from. Now, 8C5, not a really large number. This is going to be 56. 60C5, that's a big number. It is 5, 4, 6, 1, 5, 1, 2. So that'd be what? 5,461,512 ways to choose our 5 cards out of that box of 60. Now, you can simplify this on your calculator if you want. This is going to be 1 over 97527. If you want to use, if you use your calculator, I don't think it's even going to give you this. I think I Googled this. I typed this in the computer and got the simplified fraction. What the calculator did, it gave me scientific notation, which was 1.03. And then in calculator speak, it's going to be e negative 5, which really means 1.03 times 10 to the negative 5th power. Now, if we're going to expand this into standard form, this would be 0.0000103, which is a really large, actually really small number. That'd be 0. Let's see if we move it 2 to the right. There are 2 zeros and then 103%. So the probability that the 5 cards you pick all have errors is incredibly small. You got about a 1/1000th of 1% chance of this happening. So this would be like 1 in a million draws. If you drew maybe 100,000 actually, because this is let's see, tenths, hundredths, thousands, 10,000ths, 100,000. So if you drew, if you did this experiment 100,000 times, it's probably likely that one time you would have all 5 cards with errors on them. That's kind of what that tells you. Okay, sometimes it's easier to do an example like this, not necessarily this one, but there are examples where it's easier to do this when we think about opposites. And this specifically, I'm talking about complementary events. Complementary events, it is a vocabulary term. Complementary events are events whose probabilities add up to 1, and they got to be talking about the same experiment, okay, flipping a coin or drawing a card. So complementary events would be like flipping a heads and flipping a tails, or drawing a queen and drawing a card that's not a queen. Now, they don't have to be the same number. So this would be 50-50. Obviously, this one is not 50-50. This would be 1 over 13, and this would be 12 over 13. But still, they add up to 1, and that's the key part here. Okay, so we can use that to come up with an answer that's a little easier to find rather than maybe having to do a little extra work, or in some cases, a lot of extra work. So, got an example here. A production line supervisor knows that 4 out of 100 whatnots, and that's an item that the book uses. It's not something I created. I've seen gizmos. I've seen other different things. Whatnots is what we're going with. So, production line supervisor knows that 4 out of the 100 whatnots manufactured during a particular shift are defective. If 8 whatnots are randomly selected, what's the probability that at least one of them is defective? All right, so what I think we should do, since we just talked about complements, is we should probably use complements, or use the idea of complements to figure out this problem. So if we take the probability that none are defective and add the probability that at least one defective, what should we get? We should get 1, because it's either at least 1 or none of them. That would be all of the possible outcomes. So what we can say is that these two events, complements, at least 1 defective and none defective, are complements. So we can use basic algebra skills here. If we're looking for the probability that at least one of them is defective, if we want to get this one by itself, all we need to do is move this to the other side of the equation. So we can say that the probability that at least 1 is defective, at least 1 with a defect, is equal to 1 minus the probability that none are defective. And probability that none is defective is pretty darn easy to find. Now, if we wanted to find this without using complements, we can do that. We'll actually probably do that. Do something like this later on in chapter 12. Check that, chapter 13. We're in chapter 13 here. But this way just seems to go a little bit easier. So let's try to figure this out. The probability that at least one is defective is equal to 1 minus the probability that none are defective. So the first part, well, that's pretty easy. It's going to be a 1 minus the probability that none are defective. So of the ones that are not defective, we know that 4 are defective, which means 96 of them are not, and we're choosing 8. Okay, so what I'm going to say here is we're going to do 96 because we have 96 working ones, and we need to select 8 of them because we know that none of them are going to be defective. That's what we're kind of rigging the deck to say, or rigging this in our favor. Now, the probability, so this is the way we choose choose 8 of the working ones. So choose, I'm going to write this off to the side, choose 8, we'll say non-defect. And on the bottom, the total number of outcomes, this is choose 8 whatnots. Okay, and that's going to be 100 C8 because we have to take into account all of the whatnots made during that shift. Okay, so that's our two parts of our fraction, 96 C8 and 100 C8. 96 C8, 100 C8, massive numbers. I'm talking like, 100 C8 is in the trillions. 96 C8 also in the trillions. I'm not going to write those out. If you want to do it on your calculator and figure it out for yourself, or do it on the computer, that's fine. Bottom line is it's this. It's going to be 1 minus 96 C8 over 100 C8 is roughly 0.713. Now, if we do 1 minus 0.07 or 0.713, that's pretty darn easy. That's about 0.287, which would be something along the lines of 28.7%. So if we were to pick 8 whatnots from our 100 that we produced during our shift, we get about a 29% chance that at least one of them doesn't work. Now, that's the basic overview of probability. The title of the section was probability and odds. So let's visit about odds real quick. Odds, we don't use odds a whole lot in mathematics. You see odds like when we're talking about gambling again, but the odds that we talk about really aren't the same. They're not used a whole lot. I'm not a big fan of odds because it's not something we're very familiar with, very comfortable with. So we touch on it, but I'm not going to spend a whole lot of time on it. The odds is basically, or what it is, it's a ratio comparing probability of success to probability of failure. Now, if you look in the textbook for the formula for odds, it looks like this: probability of success over the probability of a failure. Okay? I don't really like this formula because it adds an extra step. To me, the odds is calculated by just taking the number of successful outcomes in an experiment over unsuccessful outcomes. Unsuccessful outcomes. That, to me, eliminates an extra step in this formula. I like this one better. Successes over failures, and that's going to give you the odds. So I got one example here for odds. A game contains 24 cards that say move ahead 1 space and 10 cards that say go back 1 space. A card may be chosen randomly from anywhere in the deck. So question number 1 here says, what's the probability of drawing a move ahead card? So now we're still talking probability. Don't get that confused with odds yet because we haven't asked about odds. That's what question number 2 will ask. Probability. So the probability that we get a move ahead card, move ahead, is equal to, well, how many move ahead cards are there in the deck? There are 24. How many cards total in the deck? 24 plus 10, because there's 24 forward, 10 backwards. 24 plus 10 would be 34. That can be simplified into 12 over 17. They're both even, so divide them by 2. Divided that in your calculator gives you roughly 0.706 or about 70.6% chance. So about 7 out of every 10 cards that are drawn should be moving ahead in your game, whatever game this may be. Question number 2. Now we're talking about odds. What are the odds that a player will move his or her token ahead one space on any given turn? So the odds here. So the successful outcomes are, again, drawing the move ahead card. The failures would be the moving backwards card. So there's 24 move ahead cards. There are 10 non-move ahead cards, or we can say move backward cards. So 24 over 10. Again, this is something that can be simplified into 12 over 5. Now, this just tells you kind of the ratio of how many successes over how many failures. It doesn't really give you a percent. I think we're most of us are familiar with these percentages. You know, we have a 71-ish% chance of moving ahead on any given turn. Well, if we made this a decimal, this is 2.4. Does this say we should get a move ahead card 240% of the time? That doesn't really make sense to me. So that's why I'm not a real big fan of odds. I'm much more comfortable with probability, and I think hopefully you are too. We're going to spend most of our time with probability. This is probably one of the very few times we will touch on odds, maybe the only time. So, we're not going to spend a whole lot of time here. We're going to focus mainly on the probability side.